Okay, so we've done all the background for the monotone convergence theorem. So we know what increasing sequence is, we know what a decreasing sequence is, we know if a sequence is bounded above, we know if a sequence is bounded below, and we know if it's bounded. Okay, so as long as you know those things, that is all the background knowledge for the theorem. One more bit of terminology, this thing monotone. You might have not heard that before, but we'll just make a little definition here. So monotone, this is either always increasing or always decreasing. Okay, so mono, right, one, and then tone is whether it's increasing or decreasing. So none of this going up and down and up and down, none of that. It's either always increasing or always decreasing. We say the sequence is monotonic, okay, or monotone. So you might see monotonic. It means the same thing. Okay, so always increasing or always decreasing. So we can draw a little picture of this before we start with the theorem. So something that's always increasing could be something like that. So it's always going up. It might level off to a constant, right? So the limit would exist because it's bounded above, but it's always going up. Okay, and then always decreasing, maybe something like this. So this one is just like a straight line going down. So in this case, it's not bounded below because it's just always going negative, but it's still always decreasing. And lastly, maybe something like this. This is neither, right? Because it goes up a bit, then down a bit, then up a bit, then down a bit. So it is not monotone. So you can put a big cross through that one. So first one is monotonic, second one's monotonic, third one is neither. Okay, please make sure you can differentiate between the three. Okay, so that's all the background we need. Let's have a look at the theorem. Every bounded and monotonic sequence so it must be bounded, it must be monotonic, is convergent. Okay, so those are the three key words you need to know. Bounded plus monotonic equals convergent. So bounded plus monotonic means it is convergent. Okay, so you must always think of that. So if you want to use the monotone convergence theorem to show that something is convergent, which we're going to do later, first you need to show it's bounded, above or below, depending on whether it's increasing or decreasing. You need to show monotone, either strictly increasing or strictly decreasing. Okay, none of this going up and down nonsense. And it must be, therefore, it's convergent. Okay, so bounded plus monotone is convergent. Now, the nice thing about this theorem is that we don't have to calculate any limits. Okay, so remember from what we did last time, if you want to show something is convergent, you need to check that the limits exist. Sometimes that's difficult, or you don't want to do it that way. This is another way of showing that it is convergent. However, the problem with this is it doesn't give you a limit value. Okay, so this method shows you that it's convergent. Okay, it is convergent, the limit exists, but we have no idea what it is. Okay, so it's a give and take between the two options. What we did last time, you directly calculate the limit, you know it's convergent, you have the limit value. Or you show it like this, you know it's convergent, it might be easier, but you have no idea what the limit is. Okay, so keep that in mind. There's a give and take between the two methods. You need to read the questions carefully to decide which one you're going to use. Okay, and the proof. Okay, so what are the two things that we know about the sequence? Number one, we know that it is bounded. That's given to us. And number two, we know it's monotonic. That's given to us. And we need to show that it must therefore be convergent. So we're going to do this in two cases. The first case is we're going to show if it is increasing and bounded above, it's convergent. And then for homework, you're going to show if it is decreasing and bounded below, it is convergent. Okay, those are the two cases. We'll do the one, you do the other. Okay, so we've got a sequence AN be a monotonic increasing sequence. Okay, so we know what that means. And bounded above. Okay, so that is bounded above. Okay, so we know it's increasing, we know it's bounded above, we need to show its convergence. And then I'll just make a note here for homework. Decreasing sequence that is bounded below. Okay, so the pink part you do for homework. Okay, so let's go back to what we're doing. We know that it is increasing and it's bounded above. That's given to us, we know for sure. Okay, so what can we get from that? Since the sequence AN is bounded above, okay, so it's bounded above. It doesn't go past some upper level. It has upper bounds. Sorry, upper bounds. Right, and we looked at that last time. So we had an increasing sequence, and we had various upper bounds for the sequence. Let S be the smallest upper bound. Okay, so again, look at the picture from last time. We have an increasing sequence. It's bounded above, so it has some upper bound. Anything above that is also an upper bound. So we look at all of the possible upper bounds, and we take the smallest. Okay, so again, please think of that picture we had from last time. Okay, then for any epsilon greater than 0, there exists a sequence element a m. So we count m elements into the sequence such that a m plus epsilon is greater than that lowest bound. So let's have a look at a little picture of what's going on here. Okay, so along the horizontal, we have n, so 1, 2, 3, 4, and so on. We know that this is increasing. We know that it's bounded above. So let's say S over there is the lowest upper bound. Okay, so all of the other upper bounds are above that. Okay, and we've got something that is increasing. Something like that. And it's getting closer and closer to S. So what we're saying over here with this element AM plus epsilon is greater than S, we're saying that somewhere along this line, there's going to be an element, let's say that one just after the pink line, that if we add any amount to it, it will be above the smallest upper bound. So here, if we add epsilon, it will then be above that line. Okay. Does that make sense? Okay. So we know that these sequence elements are getting closer and closer to S, right? Because that's the upper bound. So what that means is at some point, if I add any amount to it, it's going to go above that line. Okay, because it's getting closer and closer, never touching that line, like an asymptote. If I add an amount, it will then be above the line. Yeah?
Points like AM.
Yeah, this first one will be AM. And then the next one will be AM plus 1. So that will be M. Okay. Does everyone understand? Okay, you either ask questions or you just sit, look confused, and then fail the test. Okay. Is there anyone that does not understand what's going on with this picture? All right. Okay, so we have this point M. Anything afterwards is close enough to S such that if you add this epsilon U now, above S. Okay, so that's from the picture. Okay, since our sequence AN is increasing, right, so the first part, we use that it was bounded above. The second part, we use that it's increasing. So since AN is increasing, what do we have? For all the points after M, they must be larger than AM, right? Because it's increasing. Everything to the right of that pink line is larger than everything to the left. So we have AN is greater than or equal to AM for all N greater than or equal to M, right? It's increasing. Everything to the right of the pink line, that's the ANs to the right, is larger than everything to the left, right? Because it's increasing. Any confusion with that? No. Okay. So here we got our part 1 and 2. Okay. So again, part 1, that's from it being bounded above. And then part 2, we know that from it being increasing. So let's put the two things together. Okay, so using 1 and 2, we can write the following inequality. S minus epsilon, so we just take the epsilon over to the other side, is less than AM. Right, we just took it over to the other side there. And AM from part 2 there is less than or equal to AM. Okay. So we've got that. But remember from the beginning, over here, S is the smallest upper bound. So it's still an upper bound, it's the smallest one. So if S is an upper bound, then every element is smaller than S, right? S is an upper bound, so every element is smaller than that. So in particular, this AN is going to be less than S, because S is an upper bound. And if it's less than S, it's also less than S plus epsilon. Okay, or you could write it as less than S plus epsilon, either way. Okay, so what we're going to do from this chain of inequalities here is look at this first part. We're going to look at this middle part and the final part. We're going to put those together. Okay, so we have S minus epsilon is less than AN is less than S plus epsilon. Okay, everyone okay with that? The step that we did there? Okay. Next step, using our knowledge of absolute values, we can take this S inside the first bit, so minusing S everywhere. We get minus epsilon is less than AN minus S, less than epsilon. Okay, and we know from our absolute values that this means the absolute value of AN minus S is less than epsilon. Yep. Everyone okay with that step over there? Okay. Now, what happens when we take this in the limits when this epsilon goes to 0. What are we going to get? So we're going to take the limits for this. What do we end up with? Okay, think of it like the squeeze theorem. We got there minus epsilon on the other side. We're going to take the limits as n goes to infinity. What do we end up with? Yeah? Yeah? So what can we say about the limits of an? Non-infinity goes to? No? That difference there? S, yeah. Good. That's just from the squeeze theorem, from what we covered last year. So we take the limits, and then this a minus s gets squished till it becomes 0. So if that becomes 0, then the limits of our an sequence must be s. Okay. Now we have the limit equals s, and s is some finite value, which means it's convergent. Yeah. In fact, it converges to s, but we don't need to know that. We just need to know that it converges. Right. Any questions about this last part of the proof? No questions. Yeah.
AN.
This one.
N.
am. Because we're only interested in values after m. Because remember here, we're taking n greater than or equal to m. So here, we are only interested in values after m. Okay. Because here, after this m value, you see that gets squished up to this s. Before the m values, they're not squished up. Okay, so we want afterwards. All right. Any other questions? Okay, so for homework, you're going to do the same thing, but for the other way around. So here, you're going to start from here. So it's going to be decreasing bounded below. So here, you're going to take a sequence that's bounded below. So it will have some lower bounds. And then you can say, I don't know, L or something is the largest lower bound. And you go again. So then if you have a lower bound and you minus epsilon, then you go below. So it's all the same. And then the rest of this is the same. Okay. So you just swap it around to do the lowercase. Exactly. That's right. So you're going to take the largest lower bound. And then if you go anywhere below that, then you're underneath L or whatever you call it. So like here, if we added epsilon, it was bigger than the upper bound. Now, if you minus epsilon, you're going to be smaller than the lower bound. That's right. Okay. And then everything after that is exactly the same. Okay. Anything else? Okay. Let's have a look at some examples. So that was the proof. Well, the one part, the other part for homework. Let's look at the applications of it. So we're going to have a bunch of sequences. We're going to determine if they are convergent or divergent, but we're not going to calculate the limits. We're going to do it this way. Okay, so for homework, you calculate the limits. That's not part of what we're doing. Okay, so example 1. Let's say we have the sequence an is 1 minus 1 over n. Okay, it's very easy to calculate the limits directly, but we're not going to do that. We're going to use this monotone convergence theorem. Okay, so what do we need to show? Well, in this case, is this going to be increasing or decreasing? Just as like an initial guess, and then we'll check. So we have 1 minus something. Increasing or decreasing? Increasing or decreasing? Decreasing. Yeah, let's check. Okay, so we can use any of the methods that we looked at last time. Let's say this is a function f, 1 minus 1 over x, right? Because we want fn equals an, right? That was that third method that we looked at. Okay, let's look at the derivative. And if the derivative is strictly positive, then it's increasing. If it's strictly negative, right, then it's decreasing. That's how we can tell which one it is. Okay, what's the derivative here going to be? Hmm? 1 over 1 plus x squared. 1 over x squared. Okay, so x squared, that's always positive, right? You can put anything in there. So 1 over x squared, that's also positive. So what do we get? This is always positive. Okay, so what does that mean? Increasing or decreasing? Yeah? What negative sign? Yeah? That's gone? Because that's minus x to the minus 1. You put the minus down. Okay? Yeah, so this means it's increasing. Okay, good. Okay, it's always good to have a guess first and then check. Okay, so if it's increasing, do we need to show it's bounded above or bounded below? Above. Good. So we need to show it's bounded above. Okay, it's useless showing it's bounded below if we have an increasing function. So what can we do to show that it's bounded above? We need some upper bound that we know this will never go through. Any guesses? No, we're looking for above. Okay, no, that's a very common mistake. Mixing up upper and lower. We want something above that it never goes through. Yeah, value. So what? So 1 minus 1 over n. It never goes above what? 2. That works. Yeah, 2 works. Something else? Yeah, 2 works. This because it's 1 minus something, so it will always be less than. It's always less than what? Yeah. So, what is 1? 1 is an upper bound. 2 is an upper bound. Any other guesses? A half. No, not a half. 4, yeah, anything above. So 1, anything above, you pick any of those numbers, those will be upper bounds. Okay, let's show it for 1, and then you can try for the other numbers that you guessed. Right, you pick a number. You pick 4, and then you show that everything is less than 4. If you pick 2, you show that everything is less than 2. You can pick whatever upper bound that you want. Let's go with 1. Okay, so how can we show that everything is less than 1? Well, we know that 1 over n is always positive. Right, it's always positive. So minus 1 over n, that's going to swap. That will always be negative. And if we add 1 on both sides, we get 1 minus 1 over n is less than or equal to 1. But 1 minus 1 over n, that is our sequence, an. Okay, so we've shown that an is less than or equal to 1 for all n. So every single sequence element is smaller than 1. So 1 is an upper bound. Yeah, you can do the same thing for 2, 4, you pick any number, you can show that it will be smaller than that. Okay, so we found 1 upper bound, which means it must be bounded above. right? We just need one upper bound. That means it's bounded above. So what do we have? We have that it is increasing. We have that it is bounded above. So what can we conclude? It's convergent. So it's increasing plus bounded above. So automatically it is convergent. Yeah. And in this case, we do know what the limit is. It's going to be 1. Okay, if we take the limit, it will be 1. But we don't care about that. We just want to know if it is convergent or not. All right. Any questions on this one? Okay, let's have a look at example 2. So these next few examples, these will be your quiz type questions and your test type questions. Okay, so these will be for recursive sequences. Okay, so these sequences here, the 1 minus 1 of n, all of those were last year's stuff. You were still little babies now, babies then. Okay, you're all grown up. Now we're going to look at recursive sequences. Okay, so for the quiz and the test and so on, do not expect something like that. That is too easy. It will start from here. Okay, same for the exam. Okay, so what is a recursive sequence? A recursive sequence has some starting elements. So for this example, we have A1 is 2. And the next element will depend on the previous element. Okay, so here for this example, we have an plus 1 is equal to 1/2 of an plus 6. So it will be something like that, where the next element depends on the previous one. Okay, that's what we call a recursive sequence. Okay, so no more of those baby sequences. Okay, so we've got the sequence given. We're not interested in the limit. We'll get to that later. What we want to do is check if it is convergent or divergent. Okay, now there's a long way to do that. What you do is you take this value, you repeatedly substitute, and you try to work out the pattern. That's a lot of effort. Maybe try it out for this one. But we want to try to avoid that. Okay, so we're going to use the monotone convergence theorem. So, number 1, we need to check if it is increasing or decreasing. That will be step 1. Step 2, if it is increasing, we need to check if it's bounded above. If it's decreasing, we need to check if it's bounded below. And then we're done. From that, we can see if it's convergent. So let's write out a few terms and see. So A1 is 2. A2, what's that going to be? So you take your previous result, the current result, substitute it, and that'll give you your next result. So if A1 is 2, so there A1 is 2, what's A2? 4. A3? 5. Okay, we don't need to substitute more than that. 2, 4, 5, we suspect that it's increasing. Okay, it looks like it's increasing. Let's prove it. Okay, so how do we show if something is increasing? We need to show that the next element, an plus 1, is larger than the previous element, an. That's just from the definition. Okay, so suppose an plus 1 is greater than or equal to an. What we want to show is that the next one is larger, and then the one after that is larger, and so on. So what can we do? We have here an plus 1, and on the right here we have an. What we want to do is start from here and get to the next element. So if we look at our formula over here, okay, this includes the an, which is on the side here. What do we need to do to this right-hand side to make it look like this right-hand side? We're going to add 6. We can't just do it to one side, we have to do it to both. Okay, good. So it's almost at right-hand side. What do we have to do next? Yeah. Yeah. So what does that right-hand side become? What's this right-hand side? An plus 1. What's this left-hand side? An plus 2. Good. Okay. So let's put everything together. So from our little test thing at the top there, we've got A1 at the beginning. Everything after that was larger. Then we've got AN is less than AN plus 1. And we know AN plus 1 is smaller than AN plus 2. We didn't say what N was, so this is going to continue. So A1, that's at the beginning. We got AN plus 1 is larger, AN plus 2 is even larger. So for any N value, we've got this increasing sequence. So it's increasing. Yeah, so it's increasing. So we know it's increasing, so we need to show that it must be bounded above by something. So you can check on your calculator, you can do a few more examples, substituting back, see how the sequence goes. In fact, it's going to be bounded by 6. Okay, so again, just on your calculator, do a few more terms. You'll see it never goes beyond 6. Okay, so homework, check like 7 terms or something. You'll see it never goes above 6. So what we have is AN is less than or equal to 6. We want to try to prove that. So we're going to do a similar thing as before. We start with AN and we try to get to this AN plus 1. So we need to add 6 on both sides. Okay. And then we need the half. Okay. What's that left-hand side? AN plus 1. Okay, so we can write this out as a sequence. Our first element, A1, that was smaller than 6. So we got A1, that's smaller than 6. Any element in between, AN, is also smaller than 6. And any element after that is also smaller than 6. Yeah, because it works for any n. We didn't say what n was. So from 1 to n plus 1, anything after that, they are all smaller than 6. Okay, so the whole sequence there from A1 to infinity is smaller than 6, so it must be bounded above. Okay. So what can we conclude? First, we showed it was increasing. Then we showed it was bounded above, so it must be convergent. Okay. So what happens now if we are interested in what the limit value actually is? What can we do? Well, we know it's convergent, which means we can take the limits. The limit exists. So let's see what we get. So we've got AN plus 1 is equal to 1/2 AN plus 6. We want the limit of that, the limit of AN. So let's just take the limits on both sides. So we're going to have the limit n goes to infinity of AN plus 1 is equal to 1/2. The limit can just go inside that there. Limit n goes to infinity AN plus 6. Now in the tutorial, you're going to prove this fact here. So let's put it in pink. Limit n goes to infinity of a n plus 1 is equal to the limit as n goes to infinity a n. Okay, so in the tutorial, you're going to prove that. Okay, and we know it's convergent, so the limits exist. So we can replace the limits with L for some limit value. So we have L is equal to 1/2 L plus 6. So wherever we have the limit, we just put L because we know the limits exist. And now we just solve for L. So this will be 2L is equal to L plus 6. L is 6. Okay, so the limit is 6. Yeah, so that's one method of finding the limits. So if you've got this recursive sequence, something like this, if we know it's convergent, so like part 1 of the quiz will be show it's convergent. If we know it's convergent, then we can take the limit. We can replace the limit with L and then just solve for L. But we can't do this all the time. We can only do this if the limits exist. Okay, so it's a big warning there. Only if the limits exists. Right, you can't do it for every single recursive sequence you see. If it's a convergent sequence, then you can do this. Okay, so that's why part 1 will be show it's convergent. Part 2 will be find the limits. Okay, you'll have it like that for the quiz. Sorry? Yeah, limit value synonyms, yeah. Okay, any questions? Okay, so the quiz and the test will be set up exactly the same way. So part 1 will be show that it's increasing, for example. Part 2, show it's bounded above. Part 3, find the limits. Okay, so part 1 and part 2, you know it's convergent. Part 3, you can use this limit on both sides trick. Okay, that's exactly what you're going to get for the test. Right, any questions? No. Okay, some homework problems to try. Okay, so number 1, we've got some recursive sequences. Use the monotone convergence theorem to show their convergence, and then find the limits. Okay, like we did for these examples. So we've got a1 is root 2, and a n plus 1 is square root 2 plus a n. Okay, so that's the recursive sequence. Show its convergence, find the limits. a1 is 1, a n plus 1 is 3 minus 1 over a n, same story as the first one. a1 is 2, a n plus 1 is 1 over 3 minus a n. Okay, expect something like this for the quiz. Hint, hint. Okay, number 2. Prove that if the limit n goes to infinity of a n is 0, so we know that the sequence a n is convergent, it has limit value 0, and the sequence b n is bounded. We know what bounded means. Then the limit as n goes to infinity of a n b n is 0. Looks like a very nice exam question, or maybe a sub question. I don't know yet. Okay. And then finally, number 3. prove that. Okay, there's a lot of prove that. Okay, this chapter, the next chapter, the one after, you're going to see a lot of prove that, show that, all of those types. So prove that root 2 is equal to 1 plus 1 over 2 plus 1 over 2 plus 1 over, and so on. Yeah. Yeah, so we've got all of that. Just a little hint. Okay, so let's ignore this 1 plus, ignore all of that. If I take fraction here, what can you tell me about this bit? So look at the whole fraction and look at this bit here. What do we have? Look at the whole thing and look at this thing over here. What can you tell me about the two? It's the same. It's the same. So if this whole thing is called x, then this part is also x. So 1 over 2 plus x is x. Okay? That's your hint. If the whole thing is x, then that whole fraction there is 1 over 2 plus x, because the whole thing is x there. And then just add 1. Okay. So I'll put the hint there. What happens if this whole thing is x? Okay, and then you can put x inside there. Right. Any questions? No questions. Okay, we'll leave it at that for today. Next week, we are going to start on series. I'll tell you now so you can prepare yourselves. There are going to be 10 tests for convergence of series. So we're going to have something like this. I'm going to give you something like that. And the question is, does this converge to something or does it diverge? Okay, so that's a typical problem we're going to look at. There are 10 ways of checking. Now, with that, there are pros and cons. Okay, let's look at the cons. The cons are there's 10 things to learn, and that's a lot. Okay, you've got a lot of other work to do. It is a lot. So it is very important that you understand them and you don't just memorize all the pages. Because if you understand it and I'll show you a problem, you can use your understanding and you can solve it. If you just try and memorize everything, 2 tests that might look very similar, you're going to start confusing them. And now you get everything wrong. Okay. Because in some cases, you calculate this thing called L. If L is 1, it converges. In the other case, if L is 1, it diverges. Very easy to mix them up. Okay, so that's the con. It's a lot of work, but you chose this. Okay, now the pros. Again, there's a lot of ways to solve this. So imagine this has 7 different ways of solving it to show that it's convergent. If this is out of 5, and you go and show me 7 different ways, you now get 35 out of 5. Yeah. Now, you're not going to have time to do all 7, so you can pick. But again, if you show me 3 different ways out of the 10 tests, you get 15 out of 5. That's a lot better than 0 out of 5. Okay. So again, pros and cons. There's a lot to learn, but bonus marks. Okay. So that is going to be for next week. In your Stewart textbook under series, please read through all of the 10 tests. You don't need to memorize them just yet, but please just read through so you understand, what's being done in each case. Okay. Any questions on that? Okay, so, Saturday, just spend an hour, read through the 10, and then we'll go through that next Tuesday. Any questions?